everybody, this is Dr. Bricker here with a review for Exam 3. So Exam 3 will be Wednesday in class. You make your own formula sheet, 8.5 by 11, both sides. Put whatever you want on there. It just has to be handwritten, so no photocopies of the chapter or anything like that. Handwritten sheet. It covers Chapter 18, which is Geometric Optics, Chapter 17, which is Wave Optics, the most recent Chapter 28, which is Quantum Physics, looking at light sort of behaving like a particle, and then just a little bit of 25 through 25.7. Not the part with intensity, anything like that, just the part like describing electromagnetic waves and looking at waves as a photon. More about that as we go over the practice test. Okay, so if I were going to study for this, first I would start with the practice test. So you've had that this weekend. We're going to go over it in just a minute. You can look back at the homework. So corresponding homework would be homework 7, 8, and 9. And then you can look back through the PowerPoints. You've got videos of the classes and when we weren't there, so you can take a look through those. Read through the chapters. If you don't have time to read, completely review all these chapters, you could look at the summaries at the end of the chapters. They're pretty good as well. So hopefully when you put your formula sheet together, that's sort of a way of studying, help you to organize your thoughts. Okay, so let's actually take a look at this practice test. So the actual test is about the same length. It's multiple choice, but you do have to show your work to get credit. Okay, so looking at light in a lot of different ways. So let's just start with the first one. Monochromatic light wavelength, 550 nanometers. Okay, so 550 nanometers. Is incident normally on a diffraction grating. Okay, so that's the lab that you did, diffraction grating lab. You have to think back about that. If the third order maximum, so in other words, m is equal to 3, diffraction pattern is observed at an angle of 32 degrees. So this is 32 degrees. That's to the third order. Okay, from the center line, what is the distance between the slits in the grating? Okay. In other words, what is this? What's the size per slit? Okay, so thinking back to chapter 17, sine of theta m, this is the physics part of the whole equation, is m wavelength divided by d. We can use that actually to solve this problem because they give you the angle, they give you the order, wavelength is given. We just have to figure out this value of d here. Okay, and I'll draw a little picture in just a minute, but to solve this problem, d would be equal to m wavelength divided by the sine of theta m then. So here I've got 3, and then now be careful with the units. 550 to the -9th meters, and then I'm going to use the sine of 32 degrees to figure out what d is. Now if you notice, all these answers are in micrometers, so we'll have to turn our answer into micrometers. Okay, actually it was supposed to be 500 nanometers, not 550. So 500 nanometers, 500 nanometers. Put everything in. This comes out to be 2.83 to the -6th meters, which is a micrometer, so 2.8 micrometers. Okay. The other thing with this is to maybe take a look at what this actually looks like. So here's a screen. Here's where the diffraction grating is, just like you had in the lab. Right across, m is equal to 0. And then we had m is equal to 1, m is equal to 1. And then, correspondingly, m is equal to 2, m is equal to 2. Okay? In our problem, we actually had m is equal to 3, so let me put this here. And there would be 1 down here as well. So this is theta 3. That corresponds to m is equal to 3. And then this is the distance to the screen, L. So in addition to what you have here, again, this is the physics part of it. From the geometry of it, we could look at this angle, or any of the other angles we wanted to, and you could say that the tangent of theta m is ym divided by, so that, for example, this would be y3, this distance, divided by L. Okay, and that's purely just from the trigonometry of the whole thing. So you have both of these. You can use this one or this one. So in this problem, they might have asked you, I mean, the angle, and if they give you the distance to the screen, you could figure out the distance to the bright spots, that sort of thing. Okay, good. So not too bad. You definitely see a diffraction grading one on there. You had the lab on it after all. Okay, pivot lab. Next one, light goes from a material having an index of refraction N1 into refractive index of N2 if refracted light is bent away from the normal. Okay, so here's a surface. So light comes in here, and now it says it's bent away from the normal. So it's doing something like this. Right, here's the normal. Bending away from the normal means that this angle is bigger than this angle. This is supposed to be a straight line. Okay, so for this to happen, if this was N1 and this was N2, you bend away from the normal if N1 is bigger than N2. That's how this actually happens, right? So this could be like glass going into air, and we're bending away from the normal. So definitely have a little picture on your formula sheet about this. So draw a picture of the scenario, which I've actually done here, and then explain. I would just, sort of self-evident, the ray is bent away from the normal. This happens when N2 is less than N1, that sort of thing. Or another way of saying it, N1 is bigger than N2. This is from chapter 18, the geometric optics chapter. Just one more thing to say about this too. This whole idea is governed by Snell's law. Okay, and these angles, this would be like theta 1, and then this one could be theta 2. So you'd have N1 sine of theta 1 is equal to N2 sine of theta 2. Okay, so something like that. I mean, these go together. This idea, and then this Snell's law, if you remember Snell's law. This works in reverse too. If a ray went this way through air, it hit, say, glass, it would bend towards the normal. Okay. All right, let's look at the next one. Helium neon laser emits light 632.8 nanometers. Okay, so that's the wavelength. If the light emits 1.82 times 10 to the 17th photons per second, what is the power in milliwatts? And here's a couple of constants here. Okay, so we want the power. We want how many joules per second that we have. Okay, so let's take a look at this. You've got 1.82 times 10 to the 17th photons every second. We need to know how many joules per second we have. Okay, so we know one photon has an energy of, and you can do it the way I'm doing it, or you can figure out the energy for one photon by yourself, but the energy that a photon has would be hc divided by the wavelength. Maybe I should have written energy per photon, but that's what this is. Energy h times f, or hc over the wavelength, right? Because the speed of light is the frequency times the wavelength. So if you want, you can figure out the energy right away and just put it in here. Maybe that would be a cleaner way to do it, actually. Let's try it that way. So hc divided by the wavelength, and here's the value of h that we'll use. Okay, 6.626 to the minus 34th joules times seconds. That's h. 3 times 10 to the 8th meters per second, and then divide it by the wavelength. And that's given in the problem, 632.8, and don't forget nanometers, so times 10 to the minus 9th meters. Now, as far as the units go, you see there's a meters and a meters, they cancel out. Here's a seconds and a seconds, they cancel out. So we're left with joules. Now just be careful with all this photon stuff. Sometimes we have EV for energy, sometimes joules. Joules is the SI unit. That's what we'll actually be able to use here. So instead of writing hc over wavelength, that's what I have here. I'll just put in how much the energy for one photon is. Okay, so do this. You'll get the energy in joules, plug it back in here. Okay, and then, 1.82 times 10 to the 17th photons per second. Multiply it by how much energy one photon has. That will give you the power. And then we want it in milliwatts, so times 10 to the minus third. So here's the big key part of this. This is the way to get the energy of one photon. Okay. That's sort of a problem from the end of chapter 25. Maybe at the beginning of chapter 28. There's a lot of overlap there. Okay, so let's see. This is a geometric optics problem, it looks like. Tan's face is 20 centimeters in front of a concave shaving mirror. Okay, so a concave mirror is this. Okay, so that's the object distance. 20 centimeters. I'm not going to put it in the meters right away. I'm just going to leave it in centimeters and just see what I can do with that. If he observes his image to be twice as big and upright, okay, so twice as big and upright. They're telling us the magnification. The magnification is 2. Twice as big means it's 2. And again, it's positive, so it's an upright image. So upright and virtual always go together. It doesn't ask us that, but the fact that it's upright means it's virtual. Okay, and what we're trying to figure out is the focal length. Focal length is equal to question mark. So for lenses and mirrors, we have this. 1 over s plus 1 over s prime is equal to 1 over f. And we also have the magnification. So the magnification is minus s prime over s, which is also equal to h prime over h. So remember, s prime is the image distance. S is the object distance. H prime here is the actual height of the image. H is the height of the object. Okay? So you can notice here, if m is going to be positive, s prime must be negative. Okay? And that means it's a virtual image. Okay, so really if it's a lens or a mirror, this is what you have to work with. This and this. Those are the only 2 equations. Now this one's just a little bit tricky because usually maybe they give you s and s prime, you have to calculate f. Sometimes you have to use both equations though, which I can do for this problem. I can figure out from this equation what s prime is, and then from that I can go back to the first equation. So I'll use the second one here to figure out what s prime is. This part of it here. So m times s is equal to minus s prime. So, multiply both sides by s is equal to minus s prime. So I'm going to put a minus sign there and make this s prime then. And then I can figure out s prime. So minus 2, that's what m is. They tell you that in the problem, the magnification. Now don't be confused. M with geometric optics means the magnification. We did the first problem, the diffraction grading. That was the order of the bright spots we were talking about. Okay, and then s is given in the problem as 20 centimeters. Okay, so s prime turns out to be minus 40 centimeters then. Okay, and then we can come back here and try to figure out what f is. Okay, now it's a concave mirror, so we know that the focal length has to come out positive. The focal length of a concave mirror is positive. The focal length of a convex mirror is negative. So that's a little test here. Make sure we did this right. Okay, so let me use this equation now. So 1 over s, 1 over 20 centimeters, plus 1 over s prime. Well, s prime is negative 40, so I'm just going to put the minus sign there, is equal to 1 over f. You can do this with your calculator right now if you want to. I'm going to put this over a common denominator. So 2 over 40 centimeters minus 1 over 40 centimeters, 1 over 20 is the same as 2 over 40. That's a 4, believe it or not, is 1 over f. So this would give us 1 over 40 centimeters is 1 over f. Then I've got to invert both of them. So 40 centimeters must be equal to f. Okay, it's always a good feeling to have one of the answers there. Okay, man, that is the correct answer for this. Okay, remember I made a little sheet of sign conventions. Let's take a look at that. So I log into Brightspace. This is the videos module, chapter 18 submodule. And I didn't know where else to put it, so I just put it with the chapter 18 videos. But there's this lens and mirror sign conventions PDF. I mean, you can't just copy this and bring it. I mean, you can't print this out and bring it with you, but you could make your own little table, maybe similar to this. Or, I mean, if you want to write down this exact same thing, you can do that. But just don't, like, make a photocopy of it or something. Make your own, or, use mine as a guide. This is a mirror, concave. That's what we have here. S is always positive. S prime could be positive or negative. The focal length, though, is always positive for this kind of a mirror. Now, S prime turned out to be negative. That just meant that we were inside the focal length, and as you can see, when S prime is negative, you have a virtual upright image. Okay, good. So anyway, that's there for you. I found this again in, you go to videos, chapter 18, and I put it there for lack of any other better place to put it. Okay, let's look at the next problem. Okay, so here we have a thin film problem. A light beam wavelength 500 nanometers. Okay, so that's the wavelength in a vacuum. That's not the wavelength in the film, but just keep that in mind. Reflected constructively from a thin layer of oil having an index of refraction of, index of refraction of the film, 1.25. Let's see, the oil floats on water that has an index of refraction of 1.33. What is the minimum thickness of the layer of oil? Okay, let me draw it. I'll put this as oil. 1.33 minimum thickness. Now the thickness of the film is T. Okay, so this is the idea. Here's the film. It's physically always in the middle. This is 1.25. This is oil. I'll just put N oil. 1.33. I'm just assuming this is air up here. So light comes in. Part of it's reflected from this surface. Some of it is transmitted into the film, but then it's reflected again. Now, if you actually see it up here, it interferes constructively. So we've talked about that. This is from chapter 17. We want to know the minimum thickness of the film for constructive interference. That means you actually see it. Sometimes you might want destructive interference where you don't see it. So you've got to read this carefully. Okay, so if you look through the videos I made from chapter 17, you'll see I made a table. I'm just going to put it here so you can see it. Okay, there's a little bit of a glare. Let me turn down the lights a little bit. Okay, actually that's better. So thin films. The first thing to notice is we've got to know if there's a phase shift or not. So this little table goes through this whole idea. We've got to look at the index of refraction of the film. Now, if it's the middle value, not physically in the middle, it's always going to be physically in the middle value. In this case, it is the middle value. We have air, which is 1, oil, which is 1.33. It's the middle value. It's greater than this one, but it's less than that one. So in my table here, for constructive interference, I have this. Now, if the film had been the largest or smallest value, I would have to use this for constructive interference. And same thing over here for destructive interference. So the first thing to do with these problems is determine, is there the middle value, is it the largest or smallest value? Okay, that takes into account the phase shifts that we have going on. Okay. So now that we know that this is constructive interference, then it's not too bad to solve this problem. Just remember in this formula, 2T, M, wavelength in the film. The wavelength that they actually just gave us is the wavelength in air. So to get the wavelength in the film, you take the index of wavelength in air, divide it by the index of refraction of the film. So we have to do a little bit more work there. Okay. Turn the light back up a little bit. Okay, so again, we've determined 2T is equal to m times the wavelength in the film. If you want, you could do it like this: wavelength in the air divided by index of refraction of the film. Now, the author of the book does this too. I just put my table together, and to me, it's a little bit more concise. Minimum thickness means m is equal to 1. Any multiple thicknesses of what we're about to find works, but when m is equal to 1, that gives us the minimum thickness. Okay, so I'm running out of room here. I'm going to look at 2T is equal to 1, right, because m is 1. Wavelength in the air divided by index of refraction of the film. So let me just rewrite that over here. 2T, this is just 1. Wavelength over here, 550 nanometers, and then divided by index of refraction of the film, 1.25. It's 500. I don't know why I want to keep writing 550 today. Okay, so 500 nanometers, and then divided by index of refraction of the film, 1.25. Okay, so let's see if we could actually do this one without a calculator. T is equal to 500 nanometers then, divided by 2 times 1.25. So 500 divided by 2.5. Or maybe think about it like this. 500 divided by 2 would be 250, and then 250 divided by 1.25 would be 200. And then don't forget, we still have the nanometers, so 200 nanometers. Okay? Let's see if that makes sense. Yep, that's good. So that's the thickness, minimum thickness. And then if you have twice as big, 3 times as big, that also works. But almost all these problems say minimum thickness. Okay? Again, you don't have intuition usually in your life to do thin film problems. It's very abstract, so you really have to organize your thoughts, and hopefully you have on your formula sheet a nice little chart that looks something like this. Okay? And then you can go through and solve it. Now, let me say one more thing. If it was destructive interference and you wanted the minimum thickness, then you could put m is equal to 0 here, or m is equal to 0 here, and that would give t the smallest value. Okay? Good. All right, let's go on to the next one. What is the de Broglie wavelength? Okay, so this number 6 comes from chapter 28. What's the de Broglie wavelength of a ball of mass 200 grams? So 0.2 kilograms wavelength, moving at 30 meters per second. So remember, anything that is moving and has mass has its own wavelength. We have our own wavelength. Okay, so our wavelength is just going to be very, very small. And here's Planck's constant. Okay. Okay, so we saw in chapter 28, the momentum is h divided by the wavelength. Don't forget what momentum is, though. mv. H divided by the wavelength. So then we can solve for the wavelength. The wavelength, then move that to the left side, move mv to the other side. H over mv will give us the wavelength associated with this ball. And you can see these are very small numbers. So the ball is never going to go through anything that small. The wavelength behavior is never going to come out, just like it is for us humans. Okay, so let's put the numbers in. 6.626 to the minus 34th joules times seconds. Okay, mass, 0.2 kilograms. And then the speed, 30 meters per second. Okay, and then this answer will come out in meters. You saw some examples of us going through this before. Remember, a joule is a Newton meter, a Newton is a kilogram meter per second squared. When you put that all together, this thing will come out in meters. Okay? So put it all together. You can use your calculator if you want to. You get about 1.1 to the minus 34th. Or if you notice, 30 times 0.2 would give you 6. So you'd have 6.6 divided by 6, which would be 1.1, and then you still have to the minus 34th. Okay, so you'll see a de Broglie wavelength one. Again, that's from chapter 28, Quantum Physics. Next problem is also from chapter 28. A metal has a work function. So remember, that's the minimum amount of energy needed to liberate an electron from metal. Find the maximum kinetic energy if light of wavelength 250 nanometers shines on metal. And here's some conversion factor. 1 eV is this many joules, speed of light, Planck's constant. Okay, good. So the maximum kinetic energy that we're going to have is equal to the energy that the photon has when it's coming in minus the work function. It's kind of like balancing your checkbook. The photon comes in, it has a certain amount of energy. If you overcome the work function, you release the electron, and sometimes there's enough energy left over that you give it to kinetic energy, and then the electron has some additional speed, velocity really. Okay, so we want the answer actually in eV. Okay, so the energy that the photon has is going to be hc divided by the wavelength minus the work function. This is how much kinetic energy we have. Now I'm going to do what we did with some of our other problems, h times c. I'm going to use 1240 eV nanometers. That's what h times c is in electron volts. And then divided by the wavelength, 250 eV. So you can see the use of this. 250 nanometers. My brain worked a little bit ahead. So the nanometers cancels out, and we're left with eV. And then minus the work function. And the work function is 4.5. Okay. So 1240 divided by 250, that would be almost 5, but not quite 5. We'll have to actually do that one. Let's see if I can find my calculator really quickly. All right, looks like it's about 4.96 minus 4.5, so 0.46 or so. I rounded it up off a little bit. So hopefully this is close to it. Hopefully that's the actual answer. Okay, I checked, and yeah, that's the actual answer. So, make sure that you look back through the photoelectric effect. That's what this is called, the photoelectric effect, from chapter 28. Okay, we had this idea of cutoff frequency too. So the cutoff frequency is if you take the work function and just liberate the electron. This is something called the cutoff frequency. So frequencies lower than that, you do not liberate any electrons. Frequencies right at this amount, you liberate electrons, but you don't give them any additional kinetic energy. And then once the frequency is above the cutoff frequency, you give electrons additional kinetic energy. So take a look back through that section. Also take a look at that idea of stopping potential, stopping any electrons from drifting across. So we did one example of the photoelectric effect. Again, reminding you that you have this idea and stopping potential as well. Okay, so you'll see some variety. Not this exact problem. Maybe it would involve stopping potential, maybe cutoff frequency, that whole thing. Okay, good. So here's where we started transitioning into away from electricity and magnetism into waves. Okay, so this is a chapter 25 idea. Electromagnetic waves travels in free space as shown. If this is the electric field pointing along this direction, what is the direction of the magnetic field? So E and B are always perpendicular to each other. Turns out B has to be this way, and that's along the positive x-axis, because if you take your hand at E and you cross it over to B, your thumb gives the direction that the wave is actually traveling. So I'm E, cross over to B, my thumb is the way that the wave's traveling, and you can see it's up this way. It's hard to show this in one-dimensional piece of paper showing 3 dimensions, but imagine E, cross your fingers over to B, that's the direction that it actually travels. The other thing to remember is the speed of light. Okay, so 3 times 10 to the 8th meters per second. Doesn't matter what type of electromagnetic wave it is, radio waves, X-rays, gamma rays, visible light, they all travel at the same speed. Electric field, magnetic field part related like this, and then you know how the electric field and magnetic field part are actually related to each other. electric field part is the speed of light times the magnetic field part. They actually have the same amount of energy. It just looks like B's way smaller. It's just the choice of units that we have. Okay, so make sure you're familiar with that. As far as explaining goes, I would just say the electric field is always perpendicular to the magnetic field. E cross B gives you the direction that it's moving. That leads right into the next question. Which one of the following travels the fastest? They all travel with the same speed. And it's again kind of self-evident, but all electromagnetic waves travel at the speed of light. Okay, they just have different amounts of energy. Higher frequency means higher energy. Okay, good. So the couple of other additional 25 questions are kind of like these sort of questions. I did not put anything about intensity or anything like that from chapter 25. Power divided by area. I did not do any of those, just so you know. Just a couple like the last two. An object is placed in front of a convex lens. Okay, that's a converging lens, and it looks like this. Make sure you look back at diverging lenses. I mean, I'm just giving you an example problem, but make sure you're familiar with diverging lenses as well. An object is placed 10 centimeters in front. Okay, so that's the object distance with a focal length of magnitude 20 centimeters. Okay, so we're actually within the focal length. So if you're within the focal length, then you'll actually get an upright virtual image. What is the magnification? Okay, so again, minus S prime over S. The thing is, we don't have S prime right away. We can get it though from the lens maker's equation. 1 over S plus 1 over S prime is equal to 1 over F. So if this is the focal point, 20, that's what they're telling us. The object is actually here, inside the focal point. So whenever that happens, you'll get a virtual upright image. So the magnification should come out to be positive. Let's see if it actually does. So I'll use this equation to figure out S prime. So 1 over S prime is 1 over F minus 1 over S. So I've got 1 over 20 minus 1 over 10 when you put the numbers in. So this would be 1 over 20 minus 2 over 20. Again, if you want to just punch it in your calculator, go ahead. Minus 1 over 20, that's 1 over S prime. Whoops, sorry about that. Okay, so again, 1 over S prime, 1 over F minus 1 over S. You're just using the lens maker's equation. Then I'm putting the numbers in. Focal length is 20 minus 1 over 10. 10 is where the object is located. At this point, you can punch it in your calculator. I'm just using a common denominator. 1 over 20 minus 2 over 20. That's what 1 over S prime is again. So minus 1 over 20 when you actually do this. And then when you flip it upside down, S prime turns out to be minus 20 centimeters. Okay, again, this is negative. That means it's a virtual image, and that means it's upright. So make sure that you have all that squared away, just like that sheet that you saw before. Now the magnification is minus S prime, but S prime is also minus 20. And then divided by S, which is 10. So the magnification turns out to be 2 for this problem. Positive, meaning it's upright. Upright always means virtual. Okay, good. So let's see, that was hopefully correct. Choice A, yeah. Okay, we got a beam of light strikes a slab of transparent material. The incident beam makes an angle of 40 degrees with the normal. Okay, so this is 40 degrees. The refracted beam makes an angle of 26 with the normal. Okay, so something like this. This is 26 degrees. Okay, this is actually air up here, so I'm going to put N1 as air. And then I'll call this material N2. We don't know what N2 is. What is the speed of light in this material? Okay, so you go from air, which it's about, 3 times 10 to the 8th meters per second, into this transparent material. It's going to slow down. The speed here in this material is the speed of light divided by N2. The thing is, we don't know N2, but you can use Snell's law to figure out N2. So N1, which is 1, sine of 40 degrees is equal to N2, sine of 26 degrees. Okay, so use this to figure out N2. I'll leave it to you to do that. And then once you have N2, come over here to figure out the speed. Okay, good. So Snell's law and then a little bit extra here. The next one, the actual test will be all multiple choice. I didn't have time to put this into multiple choice form. But anyway, let's take a look at it. You'll definitely see an energy level problem. How many different wavelengths appear in the emission spectrum? Okay, so emission spectrum means you go from higher energy to lower energy. The electron goes from a higher state to a lower state. Now you can go from 3 down to 1. You can go from 3 down to 2. And then you can go from 2 down to 1. These are the allowed transitions. You can go all the way from 3 to 1, or you can go from 3 to 2, and wavelength photon will be emitted there, or you can just go from 2 to 1. Now the difference in energy that you get from doing these transitions, like say this is from 4 to 3, that would be the difference, is equal to hc divided by the wavelength. So if you wanted to, you could figure out the wavelength of the photon that's emitted. So that would be hc divided by the difference in energy. Okay, and again, you could use 1240 eV nanometers, and then say we're going from 3 to 2, the difference in energy would be 2.5. So that's a way to figure out the actual wavelength. Now, homework 9, you had a problem just like that, so take a look back at homework 9, to get another idea of this sort of problem. They didn't ask about this part. I'm just throwing this part in. As far as explain go, I would say you're allowed discrete jumps of energy. In this case, you can go from 3 to 1, 3 to 2, or 2 to 1. That's the situations where you would be emitting a photon. Okay, finally the last one, 2-slit experiment. Now if you notice on this practice test, I did not put a single slit problem. I won't put one on the test either. You'll have a thin film, it's 2-slit, and a diffraction grating one. So you don't have to worry about looking at the single slit. Okay, so 2-slit experiment, slit separation. Okay, D, they're telling you what this is. Interference pattern is created 2 meters away. Okay, so that's the distance to the screen. Okay, if the 7th bright fringe, m is equal to 7, on the screen is 10 centimeters away from the central bright fringe, so y7 is 7, what is the wavelength of the light? So the physics part of again is d sine theta is equal to m times the wavelength. For this specific problem, d sine theta 7 is equal to 7 times the wavelength. Okay, and here we're trying to figure out the wavelength. Okay, so this is perfectly good. D is given, 7 is given. We don't know what that angle is though. We don't know what theta 7 is. This is a little index m here. Okay, this is the physics part. Now the trigonometry part, if you will, is tangent theta m is equal to ym divided by the distance to the screen. So take a look back at that section of chapter 17 if you want a better picture of what's actually going on. Again, this is the physics part, this is the trigonometry part. So from this, you can figure out what theta 7 is. So tangent theta 7 is equal to y7 over L. So again, that's given and this is given, dot, dot, dot. Theta 7 is equal to something. Take a look at that and get theta 7. And then you can come back over to here to figure out what the wavelength is. D sine theta 7 over 7 is the wavelength. Okay, so you'll have to first get the wavelength from the trigonometry part and then go back to this equation to figure out what the actual wavelength is. Okay, we did some homework questions and other example problems on 2-slit experiment. Okay, I did it without using the small angle approximation formulas. You can do it that way till you get the same answer. Definitely have a little picture of this scenario though. Okay, good. So again, make a great formula sheet. You'll really need it for this test. Not a lot of intuition with this optics, geometric wave or quantum physics part. Okay, any questions, just shoot me an email. Talk to you soon. Bye-bye.